On a Thursday afternoon, the air above central South Carolina fractured with a sound of such intensity that, within hours, over 1,400 people had filed reports with the federal government. The concussive force was powerful enough to make homes sway and airport hangars rattle. In a rare move, the United States Geological Survey logged the event in its official earthquake catalog under an almost never-used designation, a sonic boom. But from where did it originate? NASA confirmed it was not a meteor, and the Air Force denied any of their fighters were responsible, while the nearest fighter wing remained silent. Then, just 48 hours later, and 800 miles to the north, the sky over Boston cracked open once again. The tremor was felt from Cambridge to the tip of Cape Cod. High above, a geostationary satellite registered a flash over the Atlantic where no storm was present. Boston police, dispatched to investigate what they believed was an explosion, found nothing. This left two powerful, unexplained booms along the same coast within the same week, all under the watch of the most sophisticated atmospheric monitoring network in history. One event received a potential answer in 90 minutes. The other remains a mystery in the federal catalog, its source still unassigned. The most unsettling part of this entire affair is not the booms themselves, but the profound question that the gap between those two answers forces us to confront. We invite you to join us at Calm Space as we delve into this mystery. If you find this exploration valuable, please consider sharing it so others may also join the conversation. Our investigation begins with the boom above Boston. Shortly after 2:00 the afternoon, Eastern Daylight Time, on Saturday, the 30th of May, 2026, a solitary, dense, and percussive sound wave rolled across eastern Massachusetts, shaking the very buildings beneath it. The first reports flooded in from a vast area, originating in Cambridge, Brighton, Scituate, Winchester, Arlington, and Concord, and stretching out to Linfield, the North Shore, and even Cape Cod. Residents in homes just 30 miles apart felt the same jarring impact. The Boston Police Department sent units to the Brighton neighborhood, responding to a flurry of 911 calls from residents who described what sounded like a powerful explosion. Across the region, items tumbled from shelves. Doorbell cameras provided crucial data, capturing the audio signature of a sharp, low-frequency pressure wave that arrived in an instant before slowly dissipating into a long, deep rumble. Within 10 minutes, social media channels across the greater Boston area were alight with thousands of variations on a single, urgent question. What was that? Answering that question is a complex task, and one that, as of this recording, does not yield a simple conclusion. The honest answer, supported by the available data, is that no one knows for certain. There are, however, compelling hypotheses. A satellite detection points firmly in one direction, yet a piece of contradictory evidence from just 2 days prior points in another entirely. And woven through it all is a pattern, a temporal clustering of two major events on the same coastline in just 48 hours. This coincidence has captured national attention in a way that isolated incidents rarely do, raising the unsettling possibility of a connection. It is this web of clues and contradictions that makes the case so profoundly compelling. To understand what happened in the sky, we must first look to the landscape over which it unfolded. Eastern Massachusetts lies on the western edge of the North Atlantic, a stretch of coastline that runs from the rocky beaches of the North Shore down through the Boston Harbor Islands, across the South Shore, and out onto the long, sandy arm of Cape Cod. Within this geography, the cities and towns of Greater Boston are nested like a constellation. Boston proper sits at the center, with Cambridge across the river to the northwest, and the historic corridor cities of Lexington and Concord reaching further out. To the southeast lie the South Shore towns of Hingham and Cohasset, while the Cape Ann communities dot the northeast. This geographic layout is not just a backdrop, it is a critical tool for analysis. The way reports of a pressure wave spread across such a landscape can reveal a great deal about its origin. A wave that creates a tight footprint, with most reports clustered within a few miles of a single point, is typically consistent with a small, ground-level event. In contrast, a wave that produces a broad footprint, with reports scattered across 40, 50, or even 80 miles in multiple directions, suggests something occurred high in the atmosphere. Such a pattern indicates that the pressure radiated outward from an elevated source point with a direct line of sight to a wide swath of the surface below. The reports from the Boston event fit this second profile perfectly. They arrived from communities scattered along a radius of roughly 30 to 50 miles around the metropolitan core, with the densest cluster in the immediate Cambridge to Boston corridor and secondary clusters along the North Shore and inland. In the language of atmospheric acoustics, this footprint was the clear signature of an aerial source. The event happened in the air, not on the ground. This conclusion was reinforced by what investigators found, or rather, what they did not find. When Boston police responded to the calls in Brighton, their search for an explosion site came up empty. There was no fire, no damaged structure, and no debris field. All they encountered was a neighborhood filled with bewildered residents and a sky that, by all visual accounts, appeared entirely ordinary. Conditions were clear, with no thunderstorms within 100 miles of the Boston area. There was no lingering smoke, nor any visible contrail in the direction from which the pressure waves seemed to have come. All that remained was the sound, the shaking, the dispatch logs, and the rapidly growing list of communities that had experienced the same baffling event. The mystery was not on the ground, it was somewhere above. The first credible attempt at an explanation emerged from the meteorological community, led by a man named Eric Fisher. As the chief meteorologist at WBZ, the CBS affiliate in Boston, Fisher is one of the most respected regional meteorologists in New England. Within about 90 minutes of the boom, he publicly posted that he had consulted the United States Geological Survey's earthquake feed and found no seismic activity associated with the event, having ruled out a terrestrial cause. He suggested in that initial post that the source might have been a meteor. This was the first step toward a scientific hypothesis. By 4:30 that afternoon, just an hour after his initial post, Fisher had followed up with a more definitive statement. He had now, in his professional opinion, confirmed that a meteor was indeed the source of the boom. "Definitely a meteor causing that big boom," were his exact words, according to his post. This conclusion quickly gained traction. Within the next hour, a professional consensus began to form among East Coast meteorologists who were monitoring the event in real time. Nick Stewart, a spaceflight meteorologist who professionally covers launches and atmospheric meteor events, posted his own analysis. He characterized the event as what was likely to be a rather significant bolide, meteor entering the atmosphere. For a moment, it seemed a clear answer had been found. The entire explanation for the mysterious boom over Massachusetts, as proposed by the meteorologist Stewart, hinged on a single, pivotal piece of evidence. This crucial observation came from an instrument called the Geostationary Lightning Mapper, which is carried aboard the GOES-19 satellite. As the newest of the National Oceanic and Atmospheric Administration's geostationary weather satellites, its data is considered highly reliable. Within minutes of the reported boom, this instrument had registered a flash over the Atlantic Ocean, east of the Massachusetts coast. Critically, this flash was not associated with any storm activity. The skies over the region were largely clear at the time. The signature of this event, as interpreted by Stewart and quickly adopted by the regional meteorological community, was consistent with a bolide. A bolide is the technical term for an exceptionally bright meteor that explodes in the atmosphere as it heats up during its fiery descent. When such an object is large enough and its trajectory is steep, the energy from its fragmentation can produce a powerful pressure wave that propagates outward. When that wave reaches the surface, it is perceived as a sonic boom, because in every meaningful technical sense, that is exactly what it is. This remains the leading hypothesis for the Massachusetts event. A bolide entered the atmosphere, broke apart high in the troposphere east of the coast, and sent a pressure wave westward that reached the Boston metropolitan area just seconds later. While the geostationary lightning mapper saw the flash, the American Meteor Society's Fireball reporting system began collecting eyewitness accounts from residents across the region. Within a remarkable 90 minutes, the professional community had a coherent explanation, and the immediate question shifted from times what times it was to times where times it came down, and how large the original object might have been. But this neat and tidy explanation is complicated by a piece of the story that does not fit cleanly into the bolide narrative. It is this detail that transforms an interesting, isolated event into something that has the rest of the country watching the eastern seaboard with a particular intensity. Just 2 days earlier, on Thursday, the 28th of May, 2026, at 5:24 inches the afternoon Eastern Daylight Time, an almost identical event had occurred 800 miles to the south, over the Midlands of South Carolina. That boom rattled buildings across more than 100 miles of geography and prompted 1,454 felt responses on the federal "Did You Feel It?" survey system. It was significant enough to generate a unique event identifier in the United States Geological Survey catalog. Yet, the federal agencies that should have been able to identify its source ruled out every conventional possibility without ever specific cause. The South Carolina event remains, officially, unexplained. The Federal Earthquake Catalog simply lists it as a sonic boom of magnitude 0 at a depth of 0 kilometers, located 6 kilometers north-northeast of a town called St. Andrews. The catalog page is clear about what the boom was not. It was not an earthquake. NASA confirmed it was not a meteor. The Air Force stated it was not one of their F-16s from Shaw Air Force Base. The agency closest to the epicenter, McEntire Joint National Guard Base, offered no comment at all. Then, just 48 hours later, on the same coast, during the same week, but in a different state, the sky cracked again over Boston. This unsettling parallel raises the central question that this video is built around. A question that permeates every observation from this point forward. If the vast federal infrastructure is capable of attributing one of these two powerful booms within 90 minutes, yet cannot explain the other even after 48 hours, what is the fundamental difference between them? Does this difference in disclosure tell us something about the events themselves, or does it instead reveal something about the system responsible for the attributions? The answer to this question matters. It matters for how we should interpret the event over Boston, and it matters for what we should expect the next time an entry like this appears in the official catalog. To begin unraveling this puzzle, we must first look closely at the satellite that provided such a swift and public attribution for the Boston boom. The sheer speed with which a single observation from space transformed public ambiguity into a confident scientific explanation is, in itself, one of the most intriguing aspects of this case. Understanding what this instrument can and cannot see is the critical first step toward understanding why one of these booms received an answer, while the other is still shrouded in mystery. The satellite in question is GOES-19. The name is an acronym for Geostationary Operational Environmental Satellite, and the number 19 marks its place in a long lineage of American geostationary weather satellites that have been in operation since the 1970s. GOES-19 is the most modern of this series, having achieved operational status in 2025. It maintains a geosynchronous orbit approximately 22,236 miles above the equator. From this vantage point, it has a continuous, fixed view of the Western Hemisphere. Its instruments stare down at the same patch of Earth, the same continents, and the same oceans every second of every day. This silent sentinel is the backbone of operational weather forecasting for all of North and South America. The specific instrument that recorded the flash is called the Geostationary Lightning Mapper, or GLM. This remarkable piece of technology was first flown on GOES-16, which became operational in 2017, and it has been a standard component on every GOES satellite launched since. The mapper's function is precisely what its name implies. It maps the occurrence of lightning. It accomplishes this by taking incredibly high-speed images of the entire visible hemisphere, searching for sudden, brief flashes of light against the backdrop of the planet. The technical specifications are worth exploring, as they define the limits of what the instrument can and cannot detect. The geostationary lightning mapper captures approximately 500 images of Earth every single second. Each of these frames is analyzed by an onboard computer programmed to look for brightness anomalies. When the computer detects a sudden spike in brightness in a specific pixel that lasts for only a few frames before fading, it registers the event as a lightning flash, complete with a timestamp accurate to the millisecond and a location accurate to within a few kilometers. Throughout the life of a single thunderstorm, the geostationary lightning mapper meticulously records thousands of distinct flashes. This data builds a real-time map, revealing not only where lightning is striking, but also how a storm is growing in power. But this instrument, designed with one purpose in mind, has an unintended yet valuable consequence. Its calibration for brightness sensitivity also makes it keenly aware of other transient, brilliant events in our atmosphere, the most important of which, for our story, are bolides. When a large meteoroid, known as a bolide, enters the upper atmosphere, the friction between the object and the air heats it to a state of incandescence. If the object is massive enough, this heating triggers a rapid and catastrophic disintegration, causing the body to fragment into smaller pieces over just a few seconds. During this fragmentation, the object's immense kinetic energy is released as electromagnetic radiation, primarily in the form of visible light. From the unique perspective of a satellite in geostationary orbit, looking down upon our planet, a bolide breakup appears as a sudden, brief, and intensely bright flash. This flash can last from a few hundred milliseconds to several seconds, all without any associated storm system beneath it. This is precisely the kind of signature the geostationary lightning mapper is calibrated to detect. This is not merely a theoretical possibility. The instrument has a proven track record. In the years since it became operational, the mapper has been formally credited with multiple bolide detections. The most well-documented recent example before today occurred over Lake Erie in northern Ohio on a Sunday afternoon in March 2026. The Cooperative Institute for Meteorological Satellite Studies at the University of Wisconsin-Madison published a detailed technical analysis of that event. Their report, which is in the public record, walks through the satellite data frame by frame, illustrating the distinct flash against the cloud-free background of the lake. This analysis establishes, in peer-reviewed technical terms, that the geostationary lightning mapper aboard the GOES series satellites can, and does, see bolides. So, when the mapper registered a flash this afternoon over the Atlantic, east of the Massachusetts coastline, it immediately caught the attention of the scientific community. The detection occurred without a thunderstorm below, and at a time that was approximately coincident with the Boston boom. This led regional meteorologists to quickly reach for the bolide explanation. It is the most parsimonious theory, meaning it is the simplest and most direct fit for the evidence. The detection fits the signature, the instrument's documented capabilities, and the established precedent. It also explains the wide area over which the boom was felt in a way that other hypotheses do not. However, before we can confidently point to a cosmic origin, it is crucial to be honest about the limits of what this single piece of evidence can tell us. Like every space-based instrument, the geostationary lightning mapper is not infallible. The technical literature documents several categories of false positive detections that must be carefully filtered out before any given flash is treated as a confirmed atmospheric event. The first involves reflections from cloud tops. When sunlight bounces off the upper surface of a tall cumulus cloud at the perfect angle, the resulting glint can be bright enough to register. A similar phenomenon occurs with solar glints off bodies of water. The third category is electromagnetic interference, in which the mapper's electronics register a non-optical signal and process it as if it were a change in brightness. To account for these potential errors, the mapper's onboard processing uses filtering algorithms designed to suppress them, but these systems are not perfect. Every year, a small number of detections are later re-evaluated and found to be reflections, glints, or interference, rather than genuine atmospheric events. This cautious approach, is at the very heart of the scientific method. The standard practice in the remote sensing community is to treat any individual mapper detection as a candidate event, not a confirmed one, until it has been corroborated by independent observations from other instruments, by eyewitness accounts from the ground, or by the recovery of meteoritic debris. To understand how a potential bolide is identified, we must look at the rigorous filtering process that every signal undergoes. The pipeline that the National Oceanic and Atmospheric Administration uses for its lightning mapper data runs raw detections through several stages of automated filtering. The first stage screens out detections that occur in pixels with persistent thermal anomalies, which are typically associated with surface features. The second stage filters out any signals that do not exhibit the characteristic light curve of an atmospheric flash, a sharp rise time of tens of milliseconds, and a slower decay. A third stage cross-checks the detection against ground-based lightning networks. Detections that do not correlate with these networks are flagged as potential non-lightning events. Finally, a fourth stage cross-checks the detection against weather radar to determine if it occurred within an active thunderstorm. Only those detections that successfully pass all four filters and occur outside the footprint of an active storm are flagged for review by a human analyst. It is at this final stage that candidate bolide events typically emerge from the vast sea of data. While the satellite provides a powerful singular viewpoint from above, the full story is often pieced together by a chorus of voices from the ground. In the hours following the boom, the Boston event has already generated a rapidly growing number of public eyewitness submissions to the American Meteor Society's pending Fireball Reports queue. This queue is the standard public archive for such sightings, where individuals can submit a structured report describing what they saw, where they were, and the object's direction of travel. The Society then processes these submissions, cross-references them for consistency, and assigns a unique event identifier to fireballs with enough corroborating witnesses to be deemed a confirmed event. At the time of this recording, the submissions for the Boston event had not yet been consolidated into an official entry, a process that can take anywhere from a few hours to a couple of days. Should the American Meteor Society's analysis confirm the Boston event as a fireball, complete with an assigned identifier and a reconstructed flight path, then the bolide hypothesis would be solidified. The combination of a satellite flash, the absence of corresponding thunderstorms, attribution from the meteorological community, and a corroborated eyewitness trajectory would form an evidence chain that closes the case. It would transform a public mystery into a settled entry in the official record. However, if the Society's process yields no resolution, if witness accounts are too sparse, inconsistent, or conflict with the satellite data, the bolide theory remains just a hypothesis. This is a critical distinction. The flash alone doesn't prove the source. It only confirms that a sensor registered an event. Likewise, witness sightings alone don't establish a cause. They only prove that the public saw something. The South Carolina event from 2 days prior serves as a powerful example of what occurs when this chain of evidence fails to converge. It demonstrates what happens when satellites detect no flash, when witnesses don't consistently report a meteor, and when conventional explanations are publicly eliminated one after another. In such cases, the official catalog entry remains open, marked with an event type but lacking any source attribution. This second incident, the one in South Carolina, is precisely what compels us to examine today's Boston event with a greater sense of gravity than we might have otherwise. It provides a troubling precedent. Our story now turns to that South Carolina boom. The day was Thursday, the 28th of May, 2026. The time was precisely 24 minutes and 30 seconds past 9:00 p.m., Coordinated Universal Time. For those in the Eastern Daylight Time Zone where the event took place, this was 5:24:30 inches the afternoon. The cataloged source point was located approximately 6 kilometers north-northeast of a small unincorporated community named St. Andrews in Richland County, South Carolina, just northwest of the state capital, Columbia. This epicenter falls near South Carolina State Highway 215 and a training center known as the South Carolina Fire Academy. For the people living in the Midlands of South Carolina that evening, the experience of the boom was, by all accounts, unforgettable. The raw power of the event was captured in numerous personal testimonies. A meteorologist, Chris Jackson, was in the state at the time and described the sensation publicly just hours later. He said it felt as though someone had forcefully shoved him in the chest an instant before the sound arrived. A resident of Rem, South Carolina, about 30 miles east of Columbia, reported that their entire home seemed to bend eastward before righting itself, an experience they characterized as an airburst. At a local airport, video footage revealed the metal walls of a hangar physically rattling from the pressure wave. Across the region, doorbell cameras captured not only the audible boom, but also the brief, powerful tremor it sent through building structures, shaking them to their foundations. The geographic distribution of these felt reports was even wider than what was seen in the Massachusetts event. Submissions came from the entire Midlands region stretching from Columbia north towards Charlotte, east towards Florence and Darlington County, and south towards the Aiken area and the Georgia border. The federal "Did you feel it?" system received submissions from communities as distant as Chesterfield County, far beyond what would typically be considered the impact zone for a single atmospheric event over Columbia. This vast footprint suggests an event of enormous scale. Within the first 24 hours, the federal system had gathered a remarkable 1,454 felt response submissions. These reports were plotted across 120 distinct intensity blocks on the federal map, with a maximum reported intensity of 6 on the modified Mercalli scale. It is worth pausing on that number, as its significance is profound. The modified Mercalli scale is the standard metric used by the United States Geological Survey to characterize the perceived intensity of a seismic event. The scale ranges from 1, which is imperceptible to humans and only detectable by instruments, up to 12, representing total destruction. An intensity level of 6 is officially characterized as strong shaking. This is the point at which buildings may begin to sustain minor structural damage. Plaster can crack, furniture might move, and objects can be knocked from shelves. People who are standing often find it difficult to maintain their balance. The fact that the May 28th event generated multiple Intensity 6 reports across a footprint of more than 100 miles indicates that whatever produced this pressure wave was not a minor atmospheric disturbance. It was an event with enough energy at its source to cause real, distributed shaking across thousands of square miles of land. The United States Geological Survey responded within hours, issuing a public confirmation that the event was not an earthquake. They did this for the same reason a doctor might rule out certain conditions before providing a diagnosis to remove a major category of explanation from consideration. Analysis of the seismic waveform did not show the signature of an earthquake. That is, it lacked the pattern of a pressure wave generated by the elastic release of strain along a subsurface fault. Instead, the waveform looked like a pressure wave that had arrived at the surface from above. The signature was consistent with a sonic boom, an acoustic shock wave created by an object moving through the atmosphere at supersonic speeds, with the shock front striking the ground from the air rather than emerging from the rock below. The agency assigned the event a unique catalog identifier, US 7000 SP6M. The US prefix is standard for the United States network in the Federal Earthquake Catalog. The event was given a magnitude of 0, as magnitude scales are calibrated for earthquakes and do not yield meaningful numbers for atmospheric pressure events. Its depth was set to 0 kilometers, reflecting that the source of the pressure wave was in the air above the surface, not in the rock below. And then there is the event type field on the catalog page. On nearly every other entry, this field reads earthquake, quarry blast, or another standard descriptor. On this entry, it reads sonic boom. To find the words sonic boom as an official event type within the Federal Earthquake Catalog of the United States, is an extraordinary detail. This is the part of the story that, once you begin to investigate it, becomes a compelling anomaly that repeatedly draws you back to the catalog page, searching for an answer that isn't there. When the United States Geological Survey assigns the sonic boom designation to an event in its federal earthquake catalog, it is a decision of considerable weight. This is not a label applied casually. The vast majority of public reports about mysterious booms are logged into the "Did you feel it?" system, where they are typically resolved as minor earthquakes, equipment glitches, or other phenomena that do not receive a permanent, unique identifier. To officially catalog an event as a sonic boom signifies that the agency has determined it was a matter of public interest, with enough analytical clarity and certainty about its non-seismic origin to be entered into the permanent record. This formal classification is a declaration that something definite occurred, yet it is also where the certainty ends and a compelling mystery begins. The term sonic boom describes the physics of what happened, a powerful pressure wave generated by an object moving through the atmosphere faster than the speed of sound. It explains the effect, but crucially, it does not identify the cause. The catalog confirms the arrival of the wave, but it leaves unanswered the question of what was traveling fast enough to create it. It is this question that makes the pattern of federal disclosure so fascinating. 3 separate federal agencies, each with its own distinct mandate and chain of command, offer different public positions regarding the activity in the airspace over central South Carolina on the afternoon of May 28th at a recorded time of 24 minutes past 5. The first response came from the National Aeronautics and Space Administration. NASA stated for the record that none of its observational assets, whether based in space or on the ground, detected any fireball during the relevant time frame. This statement carries significant weight. NASA's atmospheric meteor detection network includes the highly sensitive geostationary lightning mapper instruments on its GOES series satellites, as well as the Center for Near-Earth Object Studies Fireball Network, which routinely logs even minor meteor entries across the globe. For a bolide to enter the atmosphere with enough force to be felt over a 100-kilometer area and produce an intensity 6 pressure wave, the likelihood of it evading all of NASA's detection systems is, by the agency's own assessment of its capabilities, extremely low. In this case, the absence of a detection becomes a powerful form of evidence against the meteor hypothesis. The second federal body to comment was Shaw Air Force Base, situated in Sumter, South Carolina, roughly 40 kilometers east-southeast of the event's cataloged location near St. Andrews. The base is home to the U.S. Air Force's 20th Fighter Wing, which operates the supersonic-capable F-16 Fighting Falcon. An F-16 produces a sonic boom when it exceeds the speed of sound under operational conditions. Shaw Air Force Base confirmed on the record that none of the aircraft stationed there were engaged in supersonic flight during the time of the boom. This careful, specific denial was precise. It only accounted for their own aircraft, leaving open the question of what other craft might have been transiting their operational airspace. The third federal entity that could have provided clarity was McEntire Joint National Guard Base. Located in Eastover, South Carolina, McEntire is even closer to the event, just 30 kilometers east of the St. Andrews Catalog Point. It hosts the 169th Fighter Wing of the South Carolina Air National Guard, which flies advanced F-16 Fighting Falcon Block 52 variants. These aircraft are optimized for modern combat missions and, like all F-16s, are capable of supersonic flight. In the days after the event, however, McEntire issued no public statement. There was no confirmation of supersonic activity, but also no denial. They offered no characterization of their flight operations for the afternoon of May 28th. In the world of official statements, this conspicuous silence, set against the public denials from NASA and Shaw, became its own telling piece of data. To fully grasp the event, we must also understand the landscape over which it unfolded. The geography of where the boom was felt is as important as the geography of where the aircraft are based. The catalog source point, 6 kilometers north-northeast of St. Andrews, positions the event directly over a unique terrain. Immediately to the east of St. Andrews lies the vast expanse of Lake Murray, a reservoir created in the 1920s by damming the Saluda River. This body of water stretches for approximately 40 miles and covers a surface area of about 50,000 acres. Set in the middle of this reservoir is a small landmass named Doolittle Island, which carries a name that echoes a deep and storied military past. During the Second World War, the island was used by the United States Army Air Forces as a practice bombing range. Here, crews of B-25 Mitchell bombers trained for the legendary Doolittle raid on Tokyo in 1942. Even today, on every local map and in conversations with lifelong residents, the island is still known as Bomb Island. The name is no mere coincidence. It is a direct link to a history of military aviation in this specific part of South Carolina that predates the modern Air Force itself. The sonic boom of May 28th occurred directly above this historic corridor, an area that has been an established military overflight zone for more than 80 years. But the event did not happen in a vacuum. It occurred at a nexus of complex and overlapping phenomena. It took place over an active earthquake swarm corridor that has been generating unprecedented shallow seismicity for over 4 years. And it happened directly above the geographic footprint of the Eastern Piedmont Fault System, a geological structure that remained dormant for hundreds of millions of years until it began to stir in December of 2021. The boom was an atmospheric event, layered upon a military history, layered upon a period of profound geological unrest. On a Thursday afternoon, just 2 days before the Memorial Day weekend, a powerful event shook central South Carolina. The time was precisely 2:45 p.m. This timing is significant, as it fell during a period when both regular Air Force and Air National Guard units across the eastern United States were operating at a heightened training tempo, preparing for the ceremonial duties of the upcoming holiday. This confluence of factors does not point toward any single, simple explanation for the boom. Instead, the operational and geographic context of the May 28th event means that several candidate sources were all plausible at the same time, creating a complex and layered mystery from the very first moment. It is important to approach this subject with caution, because the silence of a federal organization is not, in any formal sense, an admission of involvement. There are numerous reasons why a military base might choose not to issue a public statement regarding its operational schedule. Standard practice for both regular Air Force and Air National Guard installations dictates that flight operations conducted within authorized airspace are not typically subject to public disclosure. Supersonic flight, in particular, is governed by Federal Aviation Administration regulations that impose restrictions on altitude and flight corridors, but they do not mandate public notification for every single supersonic event. Consequently, the standard public affairs response to a media inquiry about specific flights on a specific day is often a polite redirection to the appropriate Department of Defense channel. In this context, the absence of a public statement could be consistent with a routine non-disclosure of operational details, or it could be a deliberate decision to neither confirm nor deny. The available evidence simply does not allow us to distinguish between these two possibilities. This official silence, however, stands in stark contrast to the active public engagement from both NASA and Shaw Air Force Base. It is this asymmetry that the rest of us are left to observe and question. So, let us review where things stood at the end of the first 48 hours. A powerful pressure wave had struck the Midlands region, producing a felt footprint that stretched for 100 miles and registered a maximum intensity of 6 on the modified Mercalli scale. The Federal Earthquake Catalog officially logged the disturbance as a sonic boom. In the immediate aftermath, NASA stated that the event was not caused by a meteor. Shaw Air Force Base followed, confirming it was not one of their aircraft. Yet, from McEntire Joint National Guard Base, there was only silence. Then, just 48 hours later, the sky seemed to crack open over Boston, and this time, the very same federal infrastructure was able to converge on a clear attribution in less than 90 minutes. This stark difference in response times is, in itself, the heart of the story. To understand this discrepancy, we must examine the roles of the three key agencies: NASA, Shaw Air Force Base, and the silent McIntyre. If the federal infrastructure for attributing atmospheric pressure events were a single, unified system with one agency responsible for all sources and a single decision tree for analysis, then the events in Boston and South Carolina should have yielded the same kind of resolution at a similar speed, but they did not. The reason for this is that the federal infrastructure is not one system at all. It is a layered collection of agencies, each with a specific operational mandate, its own public affairs posture, and the authority to speak only on the narrow slice of the question that falls within its jurisdiction. Grasping which agency is authorized to speak on which piece of the puzzle is the first step toward understanding what the asymmetry of disclosure between Massachusetts and South Carolina truly tells us. In the context of atmospheric pressure events, NASA's mandate is to detect and characterize objects entering our atmosphere from space. The agency operates the Center for Near-Earth Object Studies, which maintains the public Fireball and Bolide database. Alongside the National Oceanic and Atmospheric Administration, it manages the data from the Geostationary Lightning Mapper. Furthermore, NASA maintains a network of ground-based observatories and contributes to the international infrastructure for planetary defense data sharing. When a meteor enters the atmosphere with enough energy to be registered on multiple detection assets, NASA is the agency authorized to characterize it. Therefore, when the agency states on the record that no fireball was detected, this is not an admission of ignorance. It is a definitive statement, grounded in the data from its extensive instrument network. This negative finding is a positive output of the detection system, much like a clean bill of health is a positive output from a diagnostic medical test. It does not mean nothing happened. It means that by the rigorous standards of the agency's detection chain, no meteor was observed. Shaw Air Force Base, by contrast, operates under a much narrower mandate in these situations. The base is operationally responsible for the activities of its own assigned aircraft, primarily the 20th Fighter Wing's F-16 ZO. These jets fly under operational tasking from various commands, including United States Air Forces in Europe, Air Forces Africa, and the Air Combat Command, depending on the mission. When the base officially states that none of its aircraft were operating at supersonic speeds during a specific window, it is making a factual statement based on its own flight logs. This, however, is not a statement about every single aircraft in the airspace over central South Carolina. It is entirely possible that other Air Force aircraft were transiting the area under orders from other commands, which Shaw would not necessarily have visibility into. There could have been civilian supersonic test aircraft or even foreign military aircraft on training exercises in international airspace, passing through United States airspace under standard transit clearances. Shaw's denial addresses the most likely conventional source for a sonic boom in the region, its own F-16S, but it does not exhaust all conventional possibilities. Finally, we come to McIntyre Joint National Guard Base, which sits in a different category from both NASA and Shaw. As an Air National Guard installation, it operates under a hybrid chain of command that involves both state authority, through the Governor of South Carolina, and federal authority, through the National Guard Bureau and the United States Air Force. The 169th Fighter Wing is a federally recognized Air National Guard unit, but its operational tasking can originate from either the state or federal level. While its public affairs office is structurally similar to those at regular Air Force bases, the norms for disclosure are subtly different. Air National Guard units do not typically characterize their training flight operations in real time. Routine training flights, including supersonic training conducted within authorized airspace and altitude restrictions, are not subject to public notification under standard operating procedure. This bureaucratic distinction offers a plausible, non-sensational reason for its silence, and it may hold the key to understanding this entire event. When we consider the silence from the McIntyre Air National Guard base in isolation, the most reasonable conclusion is a simple one. The base likely has no public affairs mandate to comment on its daily operational schedule. This absence of a statement would then reflect routine military procedure, not a deliberate cover-up of a specific event. This is the most logical, if unexciting, interpretation, and it aligns with everything we understand about how such installations typically operate. And yet, this explanation has not quieted the speculation that has swirled over the past 48 hours. The reason for this intrigue lies in the broader pattern of federal disclosures, which, when viewed together, inadvertently drew attention directly toward that silence. NASA, for its part, chose to issue a public statement confirming a negative finding. Shaw Air Force Base did the same. Meanwhile, the United States Geological Survey officially logged the incident in its catalog, designating it a sonic boom. Each of these actions, in its own way, narrowed the focus, sharpening the public's question. What created the boom? As conventional sources were systematically ruled out, the agencies that remained silent became, by a sort of negative inference, the new focus of attention. This is not a formal or fair way to draw conclusions. An agency's silence, especially when it has no duty to speak, is not an admission of anything, but the human mind, and especially the ecosystem of social media, does not always follow formal logic. It follows patterns of attention. In this case, the pattern with the most vocal agencies issuing specific denials, and the most operationally relevant agencies saying nothing created an imbalance in the narrative, one that the data alone did not support, but that the structure of the disclosures had nonetheless built. This imbalance became even more pronounced with a subsequent event in Massachusetts, which was attributed with remarkable speed and confidence by the very same federal infrastructure that had left the South Carolina event an open question just 2 days prior. It is the structural difference between these two cases that makes them so worthy of examination. For the Massachusetts event, the geostationary lightning mapper registered a satellite-based detection within minutes. This detection was precise in its location, time, and signature, generating a clear piece of evidence. It gave the regional meteorological community something tangible to point to, something they could explain using an instrument with a documented history of detecting bolides. The data fit the felt reports from the ground in a physically coherent manner, allowing a professional consensus to form in just 90 minutes. The evidence was strong, the attribution was confident, and the system worked as it should. In the South Carolina case, however, the story was defined by an absence of evidence. The geostationary lightning mapper produced no detection at all, a fact that NASA publicly confirmed. This is a critical detail. The source of the May 28th boom did not create the distinct flash that the same satellite would so cleanly capture over Massachusetts just 2 days later. The absence of a satellite detection is not merely a lack of information. It is, in itself, a piece of evidence. It tells us that whatever occurred over central South Carolina did not produce the kind of visual and electromagnetic signature that a typical bolide would. This single fact significantly alters the list of potential causes, steering the investigation away from the candidates that a satellite flash would have confirmed. Herein lies the fundamental structural difference between the two events. The boom in Massachusetts produced clear satellite evidence, while the boom in South Carolina did not. The speed of attribution, it seems, scales directly with the strength of that evidence. The system can provide answers quickly when the data is good, but it struggles when the evidence is missing or contradictory. The truly interesting question, then, is not why one event was solved so rapidly and the other was not. The evidence, or lack thereof, explains that. The more profound question is this: what kind of source can generate a pressure wave intense enough to be felt across a 100-mile footprint, yet produce no detectable flash for our orbiting satellites? As we are about to see, the possible answers to that question are few, and they are not entirely comforting. To understand the puzzle, we must first carefully walk through the bolide hypothesis. This is the leading explanation for the Massachusetts event. and grasping what it does and does not explain is crucial for understanding the limits of applying it to the South Carolina incident. A bolide, in simple terms, is an exceptionally bright meteor that disintegrates in the atmosphere as it heats up during entry. While there is no formal size threshold that separates a bolide from a meteor, the term is generally reserved for objects whose atmospheric entry creates a flash visible to the naked eye, often even in daylight. Their energy release is also typically significant enough to be detected by satellite instruments. The Center for Near-Earth Object Studies maintains a public fireball database, logging bolide events with energies that range from hundredths of a kiloton to several kilotons of TNT equivalent. Larger events are much rarer, but they are not without precedent. The Chelyabinsk meteor of February 2013, which exploded over Russia and created a shockwave that shattered windows across several towns, was estimated as a 440 kiloton event. Going further back, the Tunguska event of 1908, which flattened a vast expanse of Siberian forest, is estimated to have had an equivalent yield of 3 to 15 megatons. Based on the reported footprint and intensity, the recent Massachusetts event is consistent with a bolide possessing a mass of perhaps a few tens of tons. Its energy release would likely be in the small fraction of a kiloton range. This is more than enough to create a clearly audible boom across a 100-mile radius and generate structural shaking powerful enough to dispatch police units. However, it is orders of magnitude below the energy of an event that would cause catastrophic damage. It is, in fact, precisely in the range of events that the geostationary lightning mapper has been documented to detect on a routine basis. From the perspective of an observer on the ground, the signature of a bolide entry follows a classic pattern. It often begins with a brilliant flash of light. This can sometimes be seen even during the day, appearing as a brief, intensely bright object moving silently across the sky. This visual precursor is a hallmark of such an event, a silent announcement of the powerful atmospheric entry to come. When a meteor or bolide enters our atmosphere, it often announces its arrival with a silent, brilliant flash. This visual event is followed by an acoustic shock wave, a powerful boom that travels outward and eventually reaches the ground. The time gap between seeing the light and hearing the sound is the event's unique signature, a delay that reveals crucial information about its entry. Observers who witness the flash frequently report the sound arriving 30 seconds, a minute, or even longer afterward. This delay is a direct function of the speed of sound and the altitude of the breakup, which for these events is usually in the range of 20 to 40 kilometers. The recent event over Massachusetts displayed all these classic characteristics. Reports included both visual sightings, logged in the American Meteor Society's pending fireball queue, and the distinct boom that echoed across the metropolitan area, creating a textbook example of a bolide entry. The evidence for the Massachusetts event becomes even more compelling when we look at the data. A flash was detected by the geostationary lightning mapper over the Atlantic, just east of the coastline. This position is perfectly consistent with an offshore breakup, where the resulting pressure wave would travel westward over the water, making landfall in the populated regions of eastern Massachusetts. The geometry of the trajectory and the nature of the signature both align. Furthermore, the instrument that recorded the flash has a well-documented history of successfully identifying previous bolide events. This confluence of evidence is why the professional meteorological community reached a high-confidence consensus on the cause within just 90 minutes. The pieces of the puzzle seem to fit together almost immediately. However, even with such strong evidence, a rigorous scientific approach requires acknowledging any missing information. For the Massachusetts event, one part of the bolide hypothesis remains incomplete. As of this recording, no large fragments have been recovered from the ground, nor has an impact site been located. It is entirely possible that the atmospheric breakup was so thorough that no significant pieces survived the journey to the surface, which is a common outcome for meteors of this size. Still, the absence of recovered material is a detail that must be noted in any complete analysis. The evidence chain will only be fully locked in when either fragments are found on the ground or when the American Meteor Society completes its witness-based trajectory reconstruction and confirms that it aligns with the satellite's flash detection. Now, let us apply this same analytical framework to the mysterious boom that occurred over South Carolina just 2 days earlier. The comparison is illuminating, as it reveals precisely why the South Carolina event remains an open question. In this case, NASA officially confirmed that none of its observational assets detected a fireball during the relevant time window. This means that whatever transpired over central South Carolina failed to produce a flash bright enough for the geostationary lightning mapper, was not visible to the region's ground-based all-sky cameras, and left no thermal signature for any of NASA's other detection systems. In technical terms, this negative finding constitutes significant evidence times against the bolide hypothesis for the May 28th event. Despite the lack of instrumental detection, there were some intriguing ground-level observations. A single eyewitness in Columbia, South Carolina, publicly posted that they saw unusual contrails radiating from a common point right after the boom, a pattern they described as being consistent with a meteor explosion. Separately, a frame from a doorbell camera seemed to capture a faint, contrail-like trail in the upper corner of the image. While these are not negligible observations, they are not, when weighed against the totality of the evidence, sufficient to override NASA's definitive negative finding. One eyewitness account and a single camera frame are evidence that something certainly happened in the sky. They are not, however, proof that the event was a bolide of the type that the geostationary lightning mapper would normally register. The most defensible technical interpretation of the South Carolina event is that whatever created the boom did not possess the visual and electromagnetic signature of a bolide energetic enough to produce the reported ground effects. The signature was simply missing. There was no flash, and the standard satellite-based evidence that would have quickly resolved the matter was not there. This is the formal distinction that separates the South Carolina mystery from the Massachusetts event. One had the expected signature, the other did not. When that signature is absent, the official catalog entry must remain open, as the system cannot confidently attribute a cause without the corresponding evidence. This brings us to a fascinating question. What kind of source could generate the South Carolina boom without producing the telltale signs of a bolide? The answers, as we are about to discover, are few. There is a piece of the South Carolina story that has been deliberately held back until now, for it is the kind of detail that, at first, sounds too neat to be anything but a coincidence. Once you know it, however, the entire May 28th event takes on a different shape. The catalogued epicenter of the boom, a location designated as 6 kilometers north-northeast of St. Andrews, sits directly inside the active footprint of an ongoing earthquake swarm. This swarm is centered near Lake Murray, a large reservoir situated about 10 miles west of the boom's source point. It began generating measurable seismic activity in February of 2026, less than 4 months before the boom, and has continued to produce multiple felt events each month throughout the spring, with the largest reaching the high magnitude 2 range and some approaching magnitude 3. The cumulative public response across all events in the swarm since February has resulted in several thousand submissions to the federal "Did You Feel It?" system, marking this as a genuinely active swarm in the language of intraplate seismology. Yet the Lake Murray swarm is not the only seismic activity in the area. Approximately 20 miles further north and east, near the town of Elgin, a separate swarm has been producing measurable seismicity since late 2021. The Elgin swarm has now been active for over 4.5 years, generating hundreds of catalogued events. Some of these have been felt across the Midlands of South Carolina, and even as far away as the Charlotte metropolitan area in North Carolina. According to the United States Geological Survey's own assessment, the rate of seismicity in the broader Midlands region since the Elgin swarm began is the highest ever measured in the historical instrumental record for this area. What makes this flurry of underground activity so remarkable is the geological setting where it is all taking place. By any geological standard, South Carolina is classified as an intraplate region. It rests deep within the interior of the North American tectonic plate, hundreds of miles from the nearest active boundary where the Earth's crust is in motion. For a comparable setting of active seismicity, one would have to look over 2,000 miles offshore to the Mid-Atlantic Ridge, a spreading center where the North American and African plates are slowly drifting apart, the eastern United States. In a conventional sense, has not been a tectonically active area for an immense span of time. The last major mountain-building event, an ancient collision that formed a Proto-Appalachian range, is known to geologists as the Appalachian orogeny. This event concluded in the late Paleozoic era, roughly 300 million years ago. Ever since, the deep structures forged during that time have remained quiet at the surface. A long history of stability that suggests a region far removed from the dramatic forces that typically shape our planet. And yet, in the Midlands of South Carolina, a profound change is underway. Those same ancient structures are now generating measurable seismic activity at the highest rates ever instrumentally recorded for this area. The swarms of tremors, concentrated around Lake Murray and the town of Elgin, are occurring along faults that are part of what the United States Geological Survey identifies as the Eastern Piedmont Fault System. This system is a vast zone of geological weakness, a scar running from Virginia down through the Carolinas and into Georgia. It marks the boundary where the metamorphic rocks of the Piedmont province meet the sedimentary rocks of the coastal plain. For 300 million years, this system has been little more than a structural memory of the Appalachian orogeny. But since December of 2021, after being dormant for all of recorded human history, it has awakened. This unusual geological behavior has not gone unnoticed. In March of 2026, both the Washington Post and the Boston Globe featured reports on this emerging pattern. The Post and Courier also published a detailed piece that characterized the swarms as the reactivation of fault systems that had been seismically silent for hundreds of millions of years. While the reactivation of ancient intraplate faults is not entirely unprecedented on a global scale, the situation in South Carolina is compelling. The sheer rate of the seismicity and the fact that it has been sustained for over 4.5 years have drawn the close attention of the structural geology community. This sustained activity raises a fundamental question. What forces are now at play to disturb such a long and quiet slumber? Into this complex picture, the event of May 28th introduces another layer of mystery. On that day, a loud boom was recorded, and its catalog point was located directly above an active strand of the very fault system that has been producing this record-breaking seismic activity. The boom itself occurred at 0 kilometers depth, meaning its acoustic shock wave arrived at the surface from the atmosphere above. In contrast, the earthquakes originating from the fault system below typically occur at depths between 3 and 7 kilometers. The two phenomena, the boom from the sky and the tremors from deep underground, were geographically aligned but structurally separated by several kilometers of crust. This spatial coincidence, a loud sound from above, mirroring the unrest below, presents a puzzle that is difficult to ignore. Could the ground itself be the source of the sound? A fascinating, though not yet mainstream, body of geophysical literature from the last 3 decades explores this very question. The proposed mechanism is called seismo-atmospheric coupling. This theory suggests that the rapid release of elastic energy along a fault deep underground can generate an acoustic emission. This sound wave then couples with the lower atmosphere through the resulting ground motion at the surface. When this acoustic signature emerges, it can sound very much like a sonic boom, but its origin is from below the Earth, not above it. It is a hypothesis that directly challenges our conventional understanding of where such sounds come from. This theory, however, has not been established as mainstream geophysics. In its official assessment of the May 28th event, the United States Geological Survey did not invoke the seismo-atmospheric coupling mechanism. The USGS catalog entry classifies the event simply as a sonic boom. In technical terms, This means it was an acoustic shock wave produced by an object moving through the atmosphere at supersonic speed, with the shock front arriving at the surface from above. The seismo-atmospheric coupling hypothesis proposes an entirely different process, one where the shock front originates from below and breaks against the surface as it travels upward through the air. These two mechanisms are not the same, painting two very different pictures of what happened that day. Distinguishing between these two possibilities requires a close analysis of the unique signature recorded by seismic instruments. The waveform of a true atmospheric sonic boom appears different from that of a seismo-atmospheric coupling event. The first arrives as a relatively clean acoustic pressure wave that has traveled through the atmosphere. The second, however, would arrive as a more complex signature, combining the initial ground motion from the seismic event with a delayed atmospheric component. The waveform analysis that led the USGS to classify the May 28th event as a sonic boom indicates that, based on the seismic data, the agency concluded the source was atmospheric. The shock wave, they determined, originated from above. Even so, we are left with a compelling coincidence. The geographic alignment of the boom with the active fault system below, all happening on the timescale of a single afternoon, is precisely the kind of occurrence that the literature on seismo-atmospheric coupling would predict might occasionally happen. Such a scenario could arise when fault activity at depth coincides with an unrelated atmospheric event above, with their acoustic signatures arriving at the surface in a sequence that may or may not be causally connected. The data points one way, but the geography and timing suggest a story that could be far more complex. It is critical to be careful here. The data we currently possess does not establish that the May 28th boom was caused by the fault system underneath. The waveform analysis points to an atmospheric source. NASA has ruled out a meteor as the cause. This leaves a conventional alternative, some form of supersonic atmospheric vehicle, most likely an aircraft. That, however, brings us back to the unanswered question of which aircraft was flying at supersonic speeds over central South Carolina at 2:45 inches the afternoon on May 28th. But the collocation of these events is on the record, and it remains geographically suggestive. This broader pattern, two active earthquake swarms along reactivating ancient faults, set against the backdrop of an unexplained sonic boom that federal agencies have yet to attribute, creates a geological puzzle that has now captured the notice of the entire country. Before we return to the central mystery, the disparity in how these two events were reported, we must explore a fascinating, though less conventional, line of inquiry. This brings us to the seismo-atmospheric coupling hypothesis, an idea that offers a potential explanation where standard theories fall short. While this concept has not yet entered the scientific mainstream, it is not mere speculation. It is a subject of genuine academic research, with a body of literature published in peer-reviewed journals over the past 30 years. This hypothesis has been the focus of dissertations and university research programs, and it presents a candidate mechanism for the kind of unexplained atmospheric pressure event observed on May 28th, one that the standard sonic boom framework simply does not account for. To understand this hypothesis, we must first revisit the fundamental physics of an earthquake. When stored elastic energy is released along a fault line, the event is almost instantaneous, happening in microseconds far faster than any human perceivable timescale. The surfaces of the fault, which may have been locked together under immense stress for years or even centuries, suddenly slip. The rock on either side of this rupture moves past the other at speeds of meters per second, over distances also measured in meters. The energy from this abrupt motion radiates outward in every direction through the surrounding rock, creating the seismic waves that are detected by seismographs. The vast majority of this energy remains trapped within the rock, propagating efficiently through the solid material of the Earth's crust and gradually dissipating. But what if not all of the energy stays underground? A fraction of it inevitably reaches the surface, where the motion of the ground itself can couple with the atmosphere. This interaction is a direct physical displacement. When the ground surges upward, it compresses the column of air directly above it. When it moves downward, it leaves behind a region of lower pressure. This push and pull generates an acoustic pressure wave at the surface, originating from the Earth below and propagating upward into the lower atmosphere. For most earthquakes, this surface coupling is far too weak to produce an audible sound. The ground motion occurs at frequencies well below the range of human hearing, and the resulting acoustic wave is too dispersed to have any noticeable effect. However, for this silent process to become an audible event, a very specific set of conditions must align. First, the earthquake's source must be relatively shallow, typically within the upper few kilometers of the crust. This proximity ensures the ground motion is strong and not significantly dampened by overlying rock. Second, the fault's geometry must produce a significant amount of vertical ground motion, as this couples with the atmosphere far more efficiently than purely horizontal movement. Third, the local crustal structure needs to be rigid, allowing it to transmit seismic energy to the surface effectively rather than absorbing it in soft sediments. Finally, the energy release must be sharp and sudden, creating a powerful acoustic impulse instead of a gentle, diffuse vibration. When these factors converge, the resulting acoustic wave can become audible at the surface, often described as a low-frequency boom, a deep thump, a distant explosion, or even a roar. Intriguingly, the geology beneath the Lake Murray and Elgin swarm corridors in South Carolina appears to meet many of these criteria. The active fault strands in this area are located at shallow depths, ranging from 3 to 7 kilometers. These faults are oriented along the structural grain of the eastern Piedmont fault system, which features both strike-slip and reverse faulting, meaning the ground movement has both horizontal and vertical components. Furthermore, the crust of the South Carolina Piedmont is composed of high-rigidity metamorphic rock, which is an efficient transmitter of seismic energy. And while the individual earthquakes in the swarm are modest in magnitude, their sustained rate suggests the local stress field is being continuously reloaded. So, what does the seismo-atmospheric coupling hypothesis propose for the events of May 28th? It suggests that under the right combination of these local conditions, the cumulative energy released from the swarm could occasionally produce surface ground motion that is sharp enough and large enough to generate an audible atmospheric signature. This sound would arrive at the surface from below, propagating up into the air, and then radiating outward. Its pattern might resemble a sonic boom, but its underlying physics would be entirely different, born from the Earth itself. It is crucial, however, to place this idea within the context of the current scientific consensus. The hypothesis is not established, and the United States Geological Survey has not invoked it to explain the May 28th event. The standard seismological interpretation, reflected in the catalog entry, is that the event was atmospheric in origin, with a shock wave arriving at the surface from above. The official sonic boom designation confirms this reading. If the agency believed seismo-atmospheric coupling were the more likely cause, the event's designation would likely be different, or the entry might include a note referencing the underlying fault system. And yet, the idea has not been dismissed entirely. It persists as a valid topic within the scientific literature. It has been examined in relation to other intraplate seismic events across the globe, including in Central Australia, within the Reelfoot Rift system of the central United States, and in the Charlevoix seismic zone of Quebec. In each of these instances, researchers have raised the question of whether some observed atmospheric pressure events could be attributed to seismo-atmospheric coupling. The conclusions have been mixed, and the consensus holds that while it is not a routine source of audible booms, it cannot be definitively ruled out for individual events where the conventional explanation is weak. This is precisely where the conventional attribution for the May 28th event begins to feel less than certain. The most common explanations have been systematically eliminated. NASA ruled out a meteor. Shaw Air Force Base confirmed it was not one of their aircraft. Another key party, McIntyre, offered no public statement. All that remains is the possibility of some other, unknown supersonic aircraft transiting the area a plausible but entirely unconfirmed scenario, leaving the door open for a deeper and more complex explanation. Beyond conventional explanations lie more unusual possibilities, including undisclosed military activities and other mechanisms not yet widely discussed. Among these is the hypothesis of seismo-atmospheric coupling, a potential link between earthquakes and audible booms in the sky. The reason this particular idea warrants our attention is the striking geographic placement of the May 28th event. The boom was reported directly above an active seismic swarm corridor, a location that has been experiencing a record-breaking series of tremors. This correlation doesn't prove the mechanism, but it presents a critical piece of the puzzle. Any complete explanation for what happened must grapple with this geographical fact. The data allows for this reading of the South Carolina event without demanding it, leaving the door open. The very fact that both conventional sources, like aircraft, and non-conventional crustal sources remain plausible is a testament to the profound uncertainty still surrounding the official record. It is this uncertainty that keeps the catalog entry open, and in the public imagination, an open case for the May 28th event forges a link to other unexplained phenomena, such as the recent event in Massachusetts, even if their underlying causes are entirely separate. To fully appreciate the seismo-atmospheric coupling hypothesis, we must consider a much broader context, one that raises questions about our understanding of the continent itself. The Eastern Piedmont Fault System is not an isolated case of unexpected seismic activity. Across the eastern United States, other intraplate fault systems have also stirred in recent decades. The New Madrid seismic zone, infamous for the catastrophic 1,811 and 1,812 earthquakes that momentarily made the Mississippi River flow backward, continues to generate small to moderate tremors that are monitored today. Similarly, the Charleston seismic zone, which caused the devastating 1,886 earthquake felt as far away as Boston, remains formally active and is under ongoing hazard assessment by the United States Geological Survey. This pattern extends further to the Charlevoix seismic zone in Quebec, the Reelfoot Rift in Arkansas, the Wabash Valley seismic zone, and the Eastern Tennessee seismic zone. All of these are active features, producing measurable seismic readings along ancient structural lines deep within the Earth's crust. The very idea that the eastern interior of the North American continent is seismically active is, in historical terms, a relatively recent scientific realization. For much of the 20th century, textbooks framed seismic hazards in North America as being almost exclusively concentrated along the western plate boundary. The eastern half of the continent was largely characterized as stable and quiet. However, instrumental monitoring over the last 4 decades has dramatically revised this picture. The eastern interior is not stable. It is loaded with accumulated stress. Ancient fault systems that weave through the Piedmont, the Appalachian foothills, and the Great Lakes region are all carrying this tension. In many areas, the rate of observable seismic activity is higher now than it was in the early days of instrumental recording. This raises a crucial question within the geology community. Are we witnessing a genuine increase in earthquakes, or are our modern, highly sensitive monitoring networks simply detecting subtle events that would have gone unnoticed in the 1960s and 70s? This geological context is what elevates the May 28th boom from an isolated curiosity to a significant data point. The event's location directly above the Lake Murray swarm corridor fits into a much larger pattern of intraplate seismic activity being recorded across the eastern half of the continent at unprecedented levels. If a mechanism like seismo-atmospheric coupling can indeed produce audible booms at the surface, then the frequency of such events would logically scale with the underlying seismic activity. Simply put, more earthquakes would create more opportunities for this coupling to occur. If the eastern interior is producing more seismic events than at any other time in the instrumental record, it follows that the statistical probability of hearing a resulting boom at the surface would also be higher than at any prior point. It is crucial to state that this line of reasoning does not establish the seismo-atmospheric mechanism as fact. It remains unproven in the formal technical literature. But this broader pattern of seismic activity provides a context in which the hypothesis becomes more relevant, not less. The current situation aligns perfectly with what this pattern would predict. The catalog entry for the event remains open. The geography of the boom is consistent with the hypothesis. Even the official response from the United States Geological Survey, which classified the event as a sonic boom but did not attribute it to this specific coupling mechanism, is what one would expect. It is standard scientific practice not to invoke speculative mechanisms that are not yet established. In this sense, the available data is exactly where the broader pattern suggests it should be. If the bolide hypothesis for the South Carolina event ultimately fails, and if seismo-atmospheric coupling is considered too speculative to be a routine source of audible booms, another candidate explanation remains. This possibility is one that could account for both the physical sensations reported on the ground and the pattern of federal disclosure, undisclosed military or aerospace test activity. This is the theory that has garnered the most attention in online discourse over the past 48 hours. It is also the one that the official silence has done the most to keep alive in the public conversation, as the absence of clear information creates a space for such speculation to grow. For more than a decade, the United States military has been pursuing an active and largely unclassified program dedicated to hypersonic flight testing. This complex initiative is not centralized. Instead, it is distributed across a network of defense agencies and aerospace contractors, each exploring a variety of vehicle designs and operational scenarios. Key components of the program are managed by entities such as the Defense Advanced Research Projects Agency (DARPA), the United States Air Force Research Laboratory, and the Army's Hypersonic and Conventional Strike Office. These agencies frequently partner with private industry leaders, including Lockheed Martin, Northrop Grumman, and Dynetics. This collaborative effort has produced a diverse family of experimental craft, including the X-60 Hypersonic Flight Research Vehicle, the AGM-183 Air-Launched Rapid Response Weapon, and the Common Hypersonic Glide Body, alongside a series of related boost glide and air-breathing systems. This web of collaboration underscores the immense strategic priority placed on mastering this frontier of flight. The sound these vehicles generate during flight tests is, in general, distinct from that of conventional supersonic aircraft, though it falls within the same broad category as a large sonic boom. A hypersonic glide body, for instance, traveling at Mach 5 or faster through the upper atmosphere, creates a pressure wave that reaches the ground not as a single sharp crack, but as a low-frequency, prolonged boom. Witnesses often describe this phenomenon as a rolling rumble that can last for several seconds. This unique acoustic signature is a direct consequence of the vehicle's flight profile, which involves different altitudes, speeds, and shockwave geometries compared to a typical supersonic jet. Yet, from the perspective of an observer on the ground, the sound can be similar enough to a conventional sonic boom that the two are not always distinguishable without specialized instrumental analysis, blurring the line between the extraordinary and the familiar. Characteristically, the Department of Defense does not pre-announce hypersonic flight tests conducted over the continental United States. These operations are shrouded in secrecy, with airspace restrictions managed through coordination with the Federal Aviation Administration, but without any public disclosure of the test schedule itself. The standard protocol involves conducting the test, processing any subsequent public noise complaints through ordinary channels, and only acknowledging the event after the fact, if at all. This pattern of disclosure is consistent with the broader practices of the Department of Defense for its more sensitive flight test activities. It raises a fundamental question about the balance between national security and public awareness when such powerful technologies are being developed. If a hypersonic flight test were indeed the cause of the boom heard over South Carolina on May 28th, the resulting pattern of federal disclosure would look almost exactly as it does. NASA, which operates outside the military chain of command for such testing, would be at liberty to confirm that its analysis found no evidence of a meteor. Similarly, Shaw Air Force Base, which flies conventional supersonic aircraft but is not directly involved in hypersonic operations, could freely confirm that its own assets were not responsible. Meanwhile, McEntire Joint National Guard Base, the installation closest to the catalogued source point and home to F-16 Fighting Falcon Block 52 aircraft, would likely have been conducting routine training or perhaps hosting transient operations from other commands. In either scenario, the base would not be expected to publicly characterize the nature of the airspace activity. The United States Geological Survey, analyzing the seismic waveform, would log the event as a sonic boom, assigning it a unique catalog identifier. This classification is based on the physics of the pressure wave, not its origin, leaving the official record open and unattributed. It is crucial to understand that this sequence of events does not constitute proof that a hypersonic test occurred. The pattern is certainly consistent with the kind of disclosure that such a test would produce, but it is also consistent with other explanations. It is entirely possible that a different supersonic aircraft was simply transiting the area on a routine flight, and a public attribution has not yet been finalized. The available data, as it stands, does not allow us to definitively distinguish between these readings. The silence in the official record leaves room for multiple interpretations. However, there is a significant feature of this pattern that warrants closer examination. In recent years, the Department of Defense's hypersonic flight test program has undergone a substantial expansion. This includes an increased pace of testing and a notable shift in its geographic distribution. Test corridors that were once confined to ranges over the Pacific Ocean now extend over the southeastern United States and the western Atlantic. During this same period, there has been a corresponding increase in public reports of unexplained booms originating from the southeastern United States. This parallel trend invites a deeper look at the context surrounding these events. The South Carolina Swarm Corridor sits geographically nestled between several active military installations. These include Shaw and McEntire in South Carolina, Fort Liberty and Marine Corps Air Station Cherry Point in North Carolina, and the wider operational footprint of Air Combat Command and Air National Guard units across the Southeast. It is within this intricate military landscape that the silence from the McEntire base must be interpreted. That silence is consistent with a policy of routine non-disclosure. At the same time, it is also consistent with the possibility that the airspace over central South Carolina was, at that particular time, hosting activity that the base is not authorized to publicly describe. The data itself does not tell us which reading is correct. The combination of expanded hypersonic testing in the region and the federal government's asymmetrical disclosure surrounding the May 28th event has produced a powerful inference among a segment of the public. The conclusion being drawn is that something is being tested in the skies over the southeastern United States, and that the public is only being partially informed about when these tests take place. It is not an inference this analysis makes, as the data does not require it. But it is important to note that this inference is being drawn, and the very structure of the federal disclosure pattern has done nothing to discourage it. This asymmetry in public engagement, where NASA and Shaw Air Force Base provide clear denials, while McEntire remains silent, has the effect of focusing public attention squarely on the question of airspace activity. It naturally narrows the field of inquiry. Whether this focusing of attention was an intended outcome by the agencies involved or simply an unintended consequence is, itself, a question that the public record cannot resolve. When we turn our attention to the more recent event in Massachusetts, the hypersonic test hypothesis fits much less comfortably. In this case, there is a specific piece of evidence that points away from a military vehicle and toward a natural phenomenon. A flash detection from the geostationary lightning mapper over the Atlantic, east of Massachusetts, strongly suggests that the source was not a hypersonic craft, but rather a bolide, a bright meteor entering Earth's atmosphere. This provides a clear contrast, demonstrating how a single piece of data can dramatically shift the most likely explanation. A hypersonic glide vehicle, moving at speeds of Mach 5 or greater through the upper atmosphere, would not ordinarily generate the kind of flash a lightning mapper is designed to see. The thermal signature from such a craft exists in a different part of the spectrum compared to the brilliant flash of a disintegrating bolide. Because the lightning mapper is calibrated for these specific visible light transients, the reading over Massachusetts provides strong evidence that the event east of Boston was an atmospheric meteor entry, not a hypersonic test. The flash is the signature of superheated air and vaporized rock as the object breaks apart. This suggests the two incidents, in South Carolina and Massachusetts, may have entirely separate origins. While the South Carolina event could plausibly be a conventional supersonic aircraft or an unannounced military exercise, the Massachusetts event aligns far more closely with the profile of a bolide. The events occurred close in time and along the same coastline, but this proximity might be nothing more than a coincidence. It is this question of coincidence, and the underlying physics, that we will explore next. Before moving on from the hypersonic test hypothesis, it is worth adding a layer of important context, as the possibility of such a test is not without precedent. Over the last 3 years, the expansion of the United States hypersonic flight program has coincided with a noticeable increase in unexplained boom reports across several regions of the country. This phenomenon echoes a much older mystery, colloquially known as the Seneca guns, a pattern of mysterious booms heard along the Carolina coast since at least the 19th century. Historically, these sounds were attributed to everything from undersea methane releases to distant thunder carried by atmospheric inversions, each theory an attempt to grasp at a rational cause for an unnerving phenomenon. Today, a modern revival of similar reports in places like central South Carolina and southeastern Virginia has tracked the growth of military test ranges and the deployment of new high-speed aircraft. While this correlation does not prove causation, it has undeniably shaped the public conversation. Paired with the official silence and the absence of a satellite flash for the May 28th event, this pattern is why a significant portion of the online discourse has gravitated toward a hypersonic explanation over a bolide. Whether this interpretation is correct is another matter, but the discourse itself is rooted in this recurring pattern of unattributed sounds along the southeastern coast. Yet, a crucial piece of this puzzle has remained at the periphery of our discussion: the sheer scale of the felt experience for both events. A sonic boom that registers as a magnitude 6 on the modified Mercalli scale, with reports of shaking felt across more than 100 miles of land, is simply not the kind of pressure wave a small, typical source can generate under normal atmospheric conditions. The immense footprint of these events pushes the boundaries of what is expected from conventional acoustic propagation, suggesting an extraordinary cause, or perhaps an extraordinary environment. This raises a fundamental question: what allowed the sound from these events to travel so far and with such intensity? The answer, it seems, lies not in the source of the sound, but in the medium through which it traveled. The entire eastern United States is currently situated beneath a powerful upper-level trough, a stable wave pattern in the upper troposphere known in atmospheric science as an omega block. When this formation settles over a continent, it can persist for days or even weeks, diverting the prevailing zonal flow around it. As we have discussed on Calm Space in other contexts this week, this single weather feature has been the dominant force shaping conditions across the region. It is responsible for the unusual injection of cold air from Canada into the Northeast, the coastal cyclone that brought May 30th snow flurries to New England, and the severe thunderstorm risk currently unfolding over the Central Plains. But it has also quietly shaped the vertical structure of the lower atmosphere in a way that is critical for understanding acoustic travel, a detail that has been largely overlooked in the public discourse, but one that holds the key to this entire mystery. To appreciate why this weather pattern is so significant, we first need to understand how sound normally behaves in the atmosphere. Under standard conditions, a sound wave generated at or near the surface expands outwards in a roughly spherical shape. As it travels, its energy spreads over an ever-increasing area, causing the sound to weaken or attenuate with distance. A loud boom at its origin quickly fades to a moderate rumble a few miles away, eventually becoming an inaudible vibration at greater distances. This is the familiar line-of-sight acoustic propagation that governs our everyday experience of sound, where obstacles and distance are its natural enemies. However, the lower atmosphere is not always so uniform. When a strong thermal inversion occurs with a layer of cold air trapped near the surface beneath warmer air, the structure of the atmosphere fundamentally changes. This inversion layer functions as an acoustic ceiling. Instead of escaping vertically, sound waves emitted from the surface reflect off this boundary and become trapped within the lower layer. This trapped wave can then travel horizontally or laterally, with far less energy loss than it would under normal conditions. The result is that a sound event can be heard with surprising clarity at much greater distances, as if channeled through a natural atmospheric duct that preserves the wave's energy. The current omega block over the eastern United States has created precisely this kind of thermal stratification. The advection of cold air from Canada has established a sharp temperature gradient in the lower troposphere, with cold air hugging the surface and warmer air resting above it. This atmospheric condition is especially pronounced along the corridor stretching from the Appalachian foothills to the Atlantic coast. Critically, this same temperature gradient, with some regional variations, extends southward through the Carolinas and into the southeastern United States. This vast, invisible architecture in the sky provides a compelling physical explanation for how two separate events, whatever their origin, could produce such extraordinarily large and widely felt acoustic footprints, tying together disparate reports into a single, cohesive atmospheric story. Over the last several days, the lower atmosphere along the entire eastern seaboard has transformed into an exceptionally effective acoustic waveguide. This atmospheric context is a critical piece of the puzzle, as it changes how we should interpret these events. In this unique configuration, any sound-producing event will be heard and felt over a much wider area than it would under normal conditions. Therefore, the extensive 100 meters felt footprint from the May 28th boom in South Carolina and the similar one from the recent Massachusetts event are not necessarily proof of a uniquely powerful source. They are also consistent with a more moderate event, like a small bolide or a standard supersonic aircraft, whose sound was simply amplified by an unusually receptive atmosphere. In essence, the atmosphere itself is doing a significant part of the work, creating a widespread response that the source itself did not have to generate. This atmospheric phenomenon has a direct and significant impact on public awareness. Because we are situated beneath a stratified atmosphere that amplifies sound, any atmospheric pressure event, whether from a meteor, military activity, or another cause, is likely to generate a public reaction far greater than the source's actual intensity would suggest. The current atmospheric setup acts as a magnifier for public attention on the ground. Events that might have otherwise been minor local news are now becoming widespread public phenomena, which helps to explain the recent increase in boom reports across the eastern United States. However, this atmospheric explanation only solves part of the mystery. It tells us why both the South Carolina and Massachusetts events had such large felt footprints, but it doesn't address the disparity in how they were officially explained. The question of propagation is distinct from the question of the source. The atmosphere explains why these became national stories instead of local oddities, but the ultimate answer about the source will come from the federal catalog, and that answer will reveal much about the system providing it. Having explored the potential physical causes, the patterns of federal disclosure, the event's geography, and the amplifying effect of the atmosphere, we can now return to the central question of this inquiry. Let us restate the puzzle that lies before us. Within a 4-8-hour period, two significant, unexplained sonic booms were detected along the U.S. East Coast. One of these events was swiftly and confidently identified as a bolide. The other, however, was officially logged with common explanations publicly dismissed, yet no alternative cause was provided. This raises a crucial question. What can we learn from this asymmetry of disclosure? The first insight this asymmetry offers is that the federal system for identifying the cause of atmospheric pressure events is not a single, unified entity. Instead, it is a distributed network of different agencies, each with its own distinct operational mission and the authority to address only a specific part of the overall question. For instance, NASA is equipped to identify meteoric sources as it manages the network for detecting objects from space. The Air Force can confirm or deny the involvement of its own aircraft by consulting its flight logs. Similarly, the National Guard can comment on its training activities, though its public affairs practices differ from the regular Air Force and typically do not involve real-time announcements about routine flights. Meanwhile, the United States Geological Survey analyzes seismic data from its ground-based instruments. Each agency provides a single piece of the larger picture, and a complete understanding only emerges when all these pieces align. The Massachusetts event serves as a perfect illustration of this system working in concert. For that boom, the pieces of the puzzle fell into place with remarkable speed. The geostationary lightning mapper registered a satellite signature consistent with a bolide. Within just 90 minutes, both NASA and the regional meteorological community reached a consensus, attributing the event to a meteor. Simultaneously, the American Meteor Society started gathering eyewitness reports of a fireball, which will likely help confirm the object's trajectory once compiled. Here, the federal data, expert analysis, and public observation all pointed to the same conclusion, resulting in a coherent and unified attribution. The official catalog entry for this event will almost certainly be closed with a confirmed meteor designation. For the May 28th event in South Carolina, however, the pieces failed to align. In stark contrast to the Massachusetts case, the official findings were a series of negations. NASA found no evidence to support the meteor hypothesis. Shaw Air Force Base reported that none of its aircraft were responsible. McEntire Air National Guard Base issued no report. The United States Geological Survey did log the event, classifying it as a sonic boom and assigning it a unique catalog ID, but could not identify a source. The resulting federal picture is therefore incomplete. While the most common explanations have been officially ruled out, no specific alternative has been ruled in. Consequently, the catalog entry for this event remains open, its type recorded, but its origin unattributed, pending the arrival of new information. This striking asymmetry in official responses, for two events on the same coast within 48 hours, is not necessarily evidence of something unusual about the sources themselves. In fact, the most defensible interpretation is that the difference in disclosure is simply a reflection of the difference in available evidence. The Massachusetts event was accompanied by clear satellite data that pointed directly to a bolide. For the South Carolina event, no such satellite evidence existed, and the conventional possibilities were eliminated without a clear alternative to take their place. Because the two incidents had vastly different evidence profiles, the speed and confidence of their official attribution scaled accordingly. And yet, this asymmetry may also reflect something more profound about the nature of the federal infrastructure itself. It demonstrates that the system is capable of remarkable speed and clarity when the evidence is unambiguous. The swift resolution of the Massachusetts boom shows a process working at its best. But the lingering questions around the South Carolina event reveal the system's limitations when faced with ambiguity, highlighting a process that can stall when the data is inconclusive, leaving a void where a clear answer is sought. When cataloging atmospheric events, the federal system can operate in two distinct modes, both of which are considered normal. It might produce a definitive catalog entry, ruling out obvious sources before promptly ceasing investigation and leaving the matter unresolved in the public record. The catalog itself is not designed to compel a final explanation within a specific time frame. Instead, its purpose is to document what is known, highlight what remains unknown, and keep the entry open until new information can either solve the puzzle or reclassify it. What we are witnessing in real time is this exact system at work, processing two events with vastly different evidentiary trails. The system is performing precisely as intended. The incident in Massachusetts is being rapidly attributed because the evidence allows for it. In contrast, the South Carolina event is being kept open because the available data does not yet justify a confident conclusion. This asymmetry is, in a formal sense, a feature of the system, not a malfunction. Yet, it is this very feature that has fueled so much public discussion around the South Carolina event over the past 48 hours. In the official language of the federal record, the catalog entry is an open question. Such open questions in federal databases invariably draw attention, becoming focal points for online discussion, community theorizing, and independent investigations by interested citizens. The fact that the entry remains open is what sustains the mystery, even after conventional explanations have been publicly explored and dismissed. The question will likely persist in some form until the catalog entry is either closed with a positive attribution or simply fades into the background as attention shifts to newer events. Ultimately, the federal record will do one or the other. The only question is which. With the context of these two past events established, a more compelling question now emerges about what we should expect to see next. The juxtaposition of these incidents reveals much about the current state of federal disclosure for atmospheric pressure phenomena, but the truly interesting puzzle lies in what the next entry in the catalog will tell us and how soon we might see it. There are broadly three categories of outcomes that could either resolve the current situation or extend the emerging pattern. The first, and most direct, would be a confirmed attribution for the May 28th event in South Carolina. This would likely manifest as a public statement from a federal agency, identifying the source of the boom and updating the catalog entry accordingly. Given the evidence that has already been ruled out, the list of potential conventional sources is limited. It could be another Air Force aircraft that was on a routine operation, with the public announcement simply lagging behind the operational record. Non-conventional candidates might include undisclosed military test activity, which would be resolved by a Department of Defense statement, or the delayed identification of an exceptionally small bolide that initially evaded satellite detection but was later found through ground-based evidence. Any of these resolutions would close the catalog entry and, in doing so, offer valuable insight into which kinds of events the federal infrastructure is willing to publicly acknowledge after the fact. A second possibility is the occurrence of an additional event of a similar nature. If a third unexplained boom were to happen along the eastern seaboard in the coming days or weeks, following a similar pattern of federal disclosure, the temporal clustering would transform from a two-event coincidence into a multi-event pattern. Such patterns are far more difficult to dismiss as mere chance, and they tend to command a different level of engagement from government agencies. For instance, if the United States Geological Survey began observing multiple sonic boom entries clustered on the eastern seaboard in a short period, it would likely pivot from analyzing individual events to analyzing the pattern as a whole, perhaps issuing a public statement to characterize the cluster. Other federal agencies would probably follow with their own public assessments, either confirming or denying their respective conventional sources for the broader pattern. The third potential outcome is a quiet fade. If no further events occur, and no public attribution for the May 28th entry is made within the next several weeks, the entry will effectively settle into the federal record as an unattributed incident. This is not an unusual fate in the catalog's history. Other sonic boom events in the federal record have remained without a confirmed source. They simply exist in the database as part of the historical record, available for future analysis but not under active investigation. If the May 28th event follows this path, it will gradually become one more entry with an event type but no source, and public attention will eventually move on leaving the question of what caused the boom formally open forever. At this point, it is difficult to confidently predict which of these three scenarios will unfold. Each one is plausible, and the current evidence does not strongly favor one over the others. What can be said is that the initial days following a federally catalogued event represent the most probable window for additional public statements from the relevant agencies. As we are currently within that window, the chance of new public information remains elevated. Typically, after about 1 week, the frequency of new agency statements declines sharply, and the entry begins its slow transition toward whichever of the three trajectories it is destined to follow. For the recent event in Massachusetts, the trajectory appears almost certain to fall into the first category of a swift, confirmed resolution. The flash detection from the geostationary lightning mapper has already provided the basis for a public attribution. The American Meteor Society will almost certainly finalize an event identifier within the next few days. While ground-based searches for fragments may or may not succeed, the absence of recovered material will not prevent the case from being closed with a meteor designation, given the strength of the satellite evidence. The Massachusetts event is on a clear path to becoming a closed case within a week, if not sooner, serving as a textbook example of the system operating at peak efficiency. The South Carolina event, however, remains on a much more uncertain trajectory. The federal disclosure pattern has already yielded public negative findings from key agencies like NASA, ruling out specific causes. But it has yet to produce the critical positive attribution that would solve the mystery. This leaves the question open, a stark contrast to the clarity emerging from the Massachusetts incident, and a quiet reminder that not all celestial events give up their secrets so easily. Any forthcoming official word on this matter is expected to originate from one of two key bodies: the Department of Defense, which could clarify questions of military airspace activity, or the United States Geological Survey, which could address whether seismic waveform analysis points to any non-standard source. A statement from either would bring us closer to a definitive explanation. In the absence of such clarification, the case remains unresolved. Yet, a fascinating element in this entire sequence is the way public attention influences the narrative's direction. Operationally, the federal catalog is managed with strict indifference to the news cycle. The responsible agencies answer to congressional oversight and their own scientific missions. However, widespread public interest does alter the timing of their communications. When an event captures the national conversation, agencies with relevant information tend to release it more swiftly than they would for a minor, local curiosity. The South Carolina event, now linked in the collective consciousness with the recent Massachusetts incident, exists in a completely different environment of public awareness than if it had remained a standalone regional report. It raises a critical question. Will this heightened focus fast-track a public explanation, or will the agencies maintain their current, more measured pace of partial disclosure? The answer is something we are about to discover. There is another crucial pattern to consider, one that helps frame what we should expect to see next. In the days immediately following a high-profile atmospheric event, there is often a sharp increase in public reports of booms across the entire region. This phenomenon is partly due to a genuine rise in event frequency, but it is also a product of what behavioral scientists term attentional contagion. Essentially, once a population is primed to listen for atmospheric anomalies, people begin to notice and report sounds that would otherwise be dismissed as simple background noise. The result is predictable. In the week after a federally catalogued sonic boom, both the United States Geological Survey and the American Meteor Society reliably see a surge in public submissions. Upon investigation, most of these reports are traced back to mundane sources, such as distant thunder, sonic booms from military aircraft on standard flight paths, or even quarry blasting and construction work that would normally go unnoticed. This predictable surge in reports presents a significant challenge. The agencies must meticulously sift through this increased volume of data to isolate the few genuine signals from the overwhelming noise. This filtering process itself can take days, or even weeks, to complete. In the immediate wake of the Massachusetts event, federal agencies are therefore likely preparing for an elevated number of boom reports originating from all along the eastern seaboard. The vast majority of these will almost certainly be resolved as routine occurrences, but it is the small fraction that defies easy explanation, the fraction that results in new catalog entries designated as sonic boom events, that will form the crucial dataset for comparison. These new, unresolved events will be the benchmark against which the incidents of May 28th and May 30th are ultimately measured. The nature of this dataset will determine the entire narrative. If the rate of unexplained boom reports returns to its baseline level within a week or so, the current cluster will likely be classified as a simple two-event coincidence. However, if the rate remains high, with more unattributed events being added to the federal catalog, then this cluster will transform into a longer-running phenomenon, one that the agencies will eventually be compelled to characterize publicly. The environment of public attention over the next several days is therefore one of the most significant factors shaping how the events of May 28th and May 30th are ultimately recorded. This creates a recursive system. Public attention drives the volume of reports, which in turn influences the rate of agency engagement. The public watches the agencies, and the agencies, operating on their own timelines, observe the public's response to their findings. The coming days will reveal which of these two events will be filed away as a closed case, and which will persist as an open question. As we conclude our exploration of these two booms along one coast in 48 hours, it is worth honestly assessing what we have figured out and what remains unknown. On one hand, we have two catalogued events with similar physical traits occurring along the same 800-mile stretch of coastline within a 48-hour window. We have one event on May 30th with a strong public attribution to a bolide, an explanation backed by satellite flash detection, immediate meteorological consensus, and a wealth of eyewitness reports. This is contrasted by the second event on May 28th, which has no public attribution. For this incident, conventional sources have been publicly ruled out by NASA and Shaw Air Force Base, and the nearest military installation, McEntire Joint National Guard Base, has opted not to comment on its operations. We also know the federal catalog uses the sonic boom event type designation for both, implying similar physics, if not similar sources. Compounding the situation is an active omega block weather pattern, propagating sound over unusual distances and magnifying the public response. And beneath it all, an active intraplate earthquake swarm in central South Carolina, right under the May 28th event's catalog point, has been producing record-breaking shallow seismicity since December 2021, a factor that geophysical literature suggests cannot be entirely excluded. And yet, for all that we have established, there is what we do not have. There is no confirmed source attribution for the May 28th event, and there is no recovered fragment from the May 30th event. These are the critical missing pieces at the heart of this unfolding story. Although satellite evidence points toward a bolide, the absence of any recovered material means we cannot definitively attribute the South Carolina event. This uncertainty is amplified by the fact that the Department of Defense has not publicly addressed whether any non-public flights were active in that airspace at the relevant time. Officially, no link has been confirmed between this incident and another in Massachusetts. They exist as two independent entries in the federal catalog. This leaves a central question hanging in the air. What produced the pressure wave on May 28th? An honest assessment of the data suggests these two events have different evidentiary profiles and may well have different origins. The Massachusetts event is almost certainly a bolide, but the South Carolina event is, in the formal sense, genuinely unexplained, an entry in the federal record without a source. The close timing of the two is most likely a coincidence, though the available data doesn't entirely rule out a connection that is currently invisible to the public. The disparity in disclosure between the two cases seems to be a reflection of the disparity in evidence, rather than a conscious choice by any agency about what to reveal. In this view, the system is performing exactly as it should. This brings us to a broader, more crucial point. The reality that our federal infrastructure can attribute one event in just 90 minutes, yet cannot attribute another after 48 hours, is itself a valuable piece of information. It speaks to the limits of public attribution and reveals that the system maintains a high standard for reaching a conclusion. When the evidence fails to meet that standard, the system does not invent an explanation simply to satisfy public curiosity. Instead, the catalog entry remains open. The question is allowed to persist. In this way, the public record honestly distinguishes between what is known and what is not, creating a structure that allows the next piece of data to expand our understanding without erasing the initial gap of uncertainty. This, in its own way, is a sign that the system is working. The catalog is not a tool for propaganda. It is a scientific and operational record designed to preserve the integrity of knowledge by being explicit about its own limitations. The fact that the May 28th event is officially logged as an open case is not, by itself, evidence for any particular theory about its source. It is, however, evidence that the federal record is accurately representing the current state of public knowledge. For some time, the rest of us will have to live with this open question. The boom on May 28th may eventually be attributed, or it may not. The boom on May 30th will almost certainly be confirmed as a bolide. These two events might turn out to be entirely independent, their temporal proximity being the kind of coincidence that the background rate of unusual atmospheric events occasionally generates. Or they could be related in a way that the public record does not yet allow us to see. In its own time, the catalog will tell us what the next entry says. In the meantime, the key takeaway is that the skies above the eastern seaboard of the United States are being watched by federal instruments, by professional meteorologists, by an active public reporting network, and by all of us paying attention from the ground. All of this watching is producing a public record. In this instance, that record is complete enough to attribute one event with high confidence, yet incomplete enough to leave another unattributed. These two facts are not in conflict. They represent the two primary operating modes of a system that is diligently doing its job. When framed most accurately, what we are observing is not a mystery being concealed from us. It is a record being assembled in real time, with the gaps in that record being honestly acknowledged. That honest gap is perhaps the most important part of the entire record. It is what tells us where the next piece of information needs to go. And that next entry, whenever it arrives and whatever it reveals, will be the moment when this open question either finds a resolution or extends into its next chapter. Until then, we are left with what we have: 2 booms, 2 states, 48 hours, 1 coast, and a federal record doing its best to tell us, as carefully as it can, what it knows and what it does not. The asymmetry in disclosure is not the source of the mystery. It is the very structure of the record. And in this case, the record is exactly as complete as the evidence allows, no more and no less. The next time the catalog updates, we will learn which of the available interpretations the federal infrastructure is willing to endorse, and the public record will become that much more complete. Until then, the question sits open, the catalog entry is live, and the eastern seaboard watches for the next data point, whatever it may be. I want to end with a final observation, because when you step back from the technical details, it reveals something profound about the era we inhabit. We live at a time when the federal infrastructure for monitoring the sky above us is more capable than at any previous moment in human history. Satellites in geostationary orbit watch every patch of the Western Hemisphere 500 times per second. Ground-based seismic networks record pressure waves with millisecond precision across the entire continental United States. Public reporting systems, like the American Meteor Society's pending Fireball reports, collect eyewitness accounts within minutes, turning the public itself into part of the detection network. The catalog entries in the United States Geological Survey database are public, searchable, and updated in near real time. And yet, Even with this extraordinarily dense information environment, an event can occur that the system, after 2 days, has not been able to publicly attribute. The event is not hidden. The catalog records it. The agencies have engaged with the question. The conventional sources have been examined. But the answer, as of right now, is not in the public record. This is the true texture of the world we live in, one where the monitoring is dense, and the public record is, above all, honest. The chasm between what a system can observe and what it can publicly attribute defines the very scope of the open question before us. Every new object added to the catalog is just one more piece of a vast, incomplete picture. This portrait of our skies may never be finished in the way the public sometimes hopes, with a clean attribution and a neatly closed file. In this sense, the federal record is more honest. It tells us precisely what it knows, while leaving the unknown open to inquiry. The next data point, whenever and wherever it appears, will be the latest entry in a chronicle that is still being written. This record is compiled by an infrastructure that watches the sky on our behalf, and in turn, we all watch that infrastructure to see what it will ultimately reveal. This is the story as it can be told at this moment. It is not the whole story, but the part we can see from inside the public record on the 30th of May 2026. The rest, it seems, is still on its way.